We conclude this module by talking a little bit about how to approach stoichiometry problems that involve a gas phase component, or perhaps an entire reaction going on in the gas phase. So our learning goal for this is to evaluate a quantitative result as a result of a gas phase reaction. We're going to look again at our stoichiometry conversion table for moles to moles conversion. Now, one thing I want to note here is that a lot of times when we're talking about a gas phase reaction, unless it's going on in the atmosphere, it's taking place in a lab, and usually the volume is fixed in that case. So you may want to pay attention to the circumstances under which a gas phase reaction takes place. Well, here's the moles to moles conversion table for stoichiometry. Again, the only conversion factor we have is the mole ratio there in the middle. So now we're going to take apart some of this so that we can make a different version that's applicable to gas phase reactions, and this is what it would look like. Now, all we've done here basically is we're given moles in the earlier case, and now we actually have to figure out how many moles there are by using the ideal gas equation. So remember, the number of moles was equal to PV divided by RT. And so that's what I've written here as P in atmospheres, V in liters, the ideal gas constant, 0.08206, which depends upon liters, atmospheres, moles, and Kelvin, and the temperature in Kelvin. So that's just a restatement of the ideal gas law where we've solved for the moles. All right, this now gives us an opportunity to start with the moles of something that we're given, and then we can use it with the mole ratio to convert to a product or some other species in the reaction. So let's do a couple of sample problems. The first one, we'll look at a sample of carbon dioxide, and we're going to say that it occupies a volume of 4.52 liters at standard temperature and pressure. So we want to know how many moles are there. So we're going to do that first half of that conversion table now. So basically it's this version of the ideal gas law, N is equal to PV divided by RT. So I'm going to have 1 atmosphere times 4.52 liters divided by 0.082 divided by 273.15. Now, you may recall in a previous video I said that whenever you see this pair of factors multiplied by one another, they always equal 22.4. So if you recognize that and you take advantage of it, you can do a shortcut to this problem and simply say that this is going to equal 4.52 divided by 22.4, or 0.202 moles. So this is the number of moles there are of carbon dioxide in that volume at set standard temperature and pressure. So now we might go a step farther and consider another sample problem which involves an actual chemical reaction. In this case, we're going to combust pentane, which is C5H12, and we're going to say that by combusting a certain amount of pentane, it produces this 4.52 liters of carbon dioxide at standard temperature and pressure. So what we want to know is how many grams of pentane were used. So remember how we approach these problems. What I have is an amount of carbon dioxide, and I can use that amount to find out how many moles of carbon dioxide I have, which we have just done. What I want is how many grams of pentane are used in the reaction. Now, I am going to need a balanced chemical equation, and as I mentioned in the previous sample problem, we figured out how many moles of CO2 there were. The balanced chemical equation that we need for this problem is given here. C5H12 plus 8 oxygen molecules goes to 5 carbon dioxides and 6 waters. Well, it's a pretty involved chemical reaction. So now when we solve the stoichiometry problem, the thing that I have is the moles of CO2, and the thing that I want is grams of pentane. So here's what it looks like. I start with 0.202 moles of carbon dioxide. I then need to convert from moles of carbon dioxide to moles of pentane, and so I'm going to use the mole ratio from the balanced chemical equation. The coefficient in front of carbon dioxide is 5, and that in front of pentane is 1, so that's a 1 to 5 mole ratio. I then need to convert it to grams of pentane, so I need the formula weight for the pentane, and if I go to the periodic table and figure that out, I should come up with 72.17. When I multiply all these things together, I'll get 2.92 grams of pentane. So it's not much different than doing a regular stoichiometry problem. The only difference is at the beginning when we have to establish how many moles of something we have. Now, at this point, you probably are wondering, what is it I need to know about gases in this course? Well, it's a fairly simple list. We've gone through most of the hard stuff that you need to know. So one of the things you will need to know is how to adapt the ideal gas equation and solve for the various quantities in it. So in other words, be able to take PV equals nRT and solve for each of those quantities in terms of the others. If you can do that, you'll be ahead of the game in general. You'll need to know the definition of standard temperature and pressure. Standard temperature is 273.15, standard pressure is 1 atmosphere. The molar volume at STP is 22.4 liters. It's a handy number to know, simply because it saves you doing some multiplication along the way. Pressure is proportional to molarity. Okay, that funny looking symbol right after the pressure sign is the proportional to sign, which just means that we can express pressure and molarity as linearly dependent upon one another, and each one can be multiplied by a constant to get the other one. The number of moles is proportional to the partial pressure. This is simply a statement of Dalton's law of partial pressures. I don't think it's a whole lot to know, but if you can get yourself comfortable with these concepts and understand how to use them in problem-solving venues, you should be just fine.